In this video, we're going to basically prove the u-substitution theorem, or more precisely, the change of variables theorem in one variable. So the theorem says, let I and j be open intervals in R, g from I to j a differentiable function with continuous derivative and f from j to R a continuous function. So what's going on is you have some interval I and some interval j, and you have some function from j to the real numbers, and then you have some function g from I to j. Okay? Then for any a and b in I, the integral from g of a to g of b of f is the integral from a to b of f of g of t times g prime of t dt. So that's the theorem. Now let's prove it. So the idea is that we're trying to show that these two numbers are equal, right? We're trying to show that this number and this number is equal and they're both integrals. And the idea is to look at the functions that are defined by these integrals and then show that they have the same derivative. And then if they have the same derivative, then they must, the difference must be a constant. And then we show that the constant is 0. So define a function capital F from j to R by capital F of t is the integral from g of a to t f of x dx. So notice that the left-hand side of this inequality that we're trying to show, this part is just capital F of g of b, right? So this function is differentiable because f was assumed to be a continuous function. So this integral exists, right, from g of a to t. So then capital F is differentiable. That's by the fundamental theorem of calculus, and f prime is little f. Okay, now define another function h from I to R by h of x equals the integral from g of a to g of x f of t dt. Okay, well, the left-hand side is just what you get when you evaluate the function at b, right? So, so then h, capital H, is f composed with g. Because if you plug in x, okay, capital H of x is capital F of g of x, right? If you just look at the definition. So you have h is the composition of two differentiable functions, and so by the chain rule, it's differentiable. So h prime of x is capital F prime of g of x times g prime of x for all x in the open interval I. So what did we show? Well, if Okay, and then this capital F prime is little f. So this is little f of g of x times g prime of x. So we have this function capital H, and its derivative is this. So therefore, it must be up to a constant defined to be the integral of that function. So h of x is the integral from a to x of f of g of t times g prime of t dt plus c for some constant c. Right? Because the derivative of this function by the fundamental theorem of calculus is just equal to little f of g of x times g prime of x. So these two functions have the same derivative, and therefore the difference must be a constant. Okay. Now this h of x, okay, h of b is equal to this, right? That's capital H of b, and we're trying to show that that's equal to this. So if we can show that c is 0, then we can just plug in x equals b and then we'll be done. Now let x equal a. So then we have capital H of a is 0 plus c, right? Because the integral from a to a is 0. So capital H of a is c. But capital H of a was defined to be the integral, but capital H of a is the integral from g of a to g of a of something, f of t equals 0. So c is 0. Therefore, h of x equals the integral from a to x of f of g of t times g prime of t dt. And now we let x be b. Okay, then we get that the h of b is the integral from g of a to g of b of the function little f, and then by what we have here, if you plug in x equals b, we get the integral from a to b of f of g of t times g prime of t dt. And that's the proof. Okay. So how is this u-substitution? Well, if you look at what we have, often you're interested in evaluating some integral like this. So it could be something like the integral of, 2x times sine of x squared dx, right? From 0 to pi over 4, let's say. And this will look like the integral on the right if we let a be 0 and b be pi over 2. And okay, I use x here instead of t, but you can use g of x is x squared, and then f of x is sine x, right? Then this integral that we're trying to calculate exactly matches on the right. And so by the theorem, this is equal to the integral of f of t, so that's sine, okay, I'll just use x, from g of a, so that's 0 squared, to pi over 2 squared, so it's pi squared over 4. And then this is going to be negative cosine of pi squared over 4 minus negative cosine of 0, so it's plus 1. Right? So this is usually called u-substitution because we let u be x squared. And then the u is the same as the g. Okay. So this u-substitution is actually a theorem, right? It's this theorem that we just proved. And this is called the change of variables theorem. Now, in calculus, they usually don't call it the change of variables theorem, but this really is a change of variables theorem. If you look at this diagram, so what's going on is you have a function from an interval to the real numbers, and it's hard to evaluate the integral, but if you have this function g from another interval to the domain of f, then you can look at the composition f composed with g and integrate that, right? That's this f of g of t, but then you have to multiply by the derivative of g. So you have to multiply by the derivative of g to get g prime of t, and then you integrate the product here. And if you look at the change of variables formula in higher dimensions, that's basically what's going on. So the u-substitution fact is, in higher dimensions, it's the change of variables formula. Okay. And this is the change of variables formula in one variable.